Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin, and I am the Technical Director at Mercury Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Luca Lucarelli. Dr. Lucarelli has more than 30 years of experience with using porosimetry, physisorption, chemisorption, and pycnometry for the characterization of materials. I've had the pleasure of working with Luca since he joined Micromeritics in 2019. Luca received an industrial chemistry degree at the Milan State University. Luca is currently a technical application consultant with Micromeritics in Europe. Luca, I know I speak for many coffee lovers. We are so glad you could be here today to share your insights on porosity and density characterization of freeze-dried organic products.
Thanks for the introduction and good morning or good afternoon to everybody. The drying techniques to preserve seasonal food are known since 12,000 BC. In the past, but even today, in many areas, natural forces such as sun and wind are still used to dry fish, meat and fruits for a later consumption. The development of modern technologies has revolutionized this method for food preservation. Drying is an effective way of providing food all year round, preserving its nutrients, and today it is a significant global industry. Despite the advantages, the drying techniques using only heat require large amount of energy, and due to the need of relatively high temperatures and long drying times, this may result in thermal degradation of the food or its nutrients and ultimately inferior quality. Freeze drying is the process by which the solvent, usually water, is crystallized at low temperature and removed by sublimation. Sublimation is the direct transition of water from solid to gas state without melting. There are three main stages in the process: preliminary drying by heating, rapid freezing, and sublimation drying. The freezing phase is the most critical step. Food should be frozen rapidly to avoid the formation of large ice crystals, which can generate large internal cavities in the food, deteriorating its quality. During the sublimation drying phase, high vacuum and heat are applied to provide the energy needed for the ice to sublime. This phase removes about 95% of the water present in the food. Temperature, time, and sequence of operations can influence dramatically the quality of the final product. The lyophilization technique is largely used today in the food, biotech, and pharma industry, but recently used in material technology as well, for instance to create stable and highly porous aerogel structures. To understand how the freeze-drying process can modify the structure of organic compounds, we will present a case study on instant coffee. Why is instant coffee so successful worldwide? Even more than Italian espresso. The speed of preparation and reduced cleanup make it ideal for use in offices, home, and automated coffee dispensers. Instant coffee has a lower shipping volume and weight, thus reducing the impact of shipping cost on the end-user price. long shelf life, finally, explains why up to 50% of the world's green coffee beans are used to produce instant coffee. Being Italian, I am a strong coffee consumer, and from time to time I drink also instant coffee in some situations, for instance when I can't find a good Italian-style espresso. I wanted first to investigate the history of instant coffee. The source is Googling Internet, thus some information might be not exactly precise, but despite a certain degree of uncertainty, the history of instant coffee is quite curious. The first clue is a coffee cake form used by soldiers during the US Civil War between 1861 and 1865. The main task was to provide soldiers with enough doses of caffeine. Historians believe that between 1880 and 1901, instant coffee was independently created in 3 different countries, in France, in New Zealand and in the US by an American-Japanese man, Mr. Satoru Kato, who applied to coffee his method to make instant tea. Kato-san presented his product at the Pan American Exposition in Buffalo between 1901 and 1910, but his product was unpopular. Kato's idea was further developed by George Constant Louis Washington, who marketed his product with the name of Red E-Coffee. His success demonstrated the importance of marketing. The real boost to the use of Washington instant coffee happened during the First World War. Purpose was again to provide an easy and rapid way for caffeine supply. Between the First and Second World War, many companies began to produce instant coffee, increasing its popularity after the Second World War. During those years, at Nestlé Research Laboratory in Switzerland, the scientist Max Morgenthaler finally developed an industrial process for drying the coffee extract and soluble carbohydrates, which were added as stabilizers. In 1954, Nestlé was able to produce instant coffee made of only coffee, that is, avoiding the addition of carbohydrates. And finally, in 1965, the lyophilization process was used for the first time to produce instant coffee. The coffee lyophilization process consists mainly in 7 steps. The parameters described hereafter are just indicative and may change depending on the process. The first step is roasting. Green beans are heated at 230 degrees for 10 minutes, then cooled rapidly to 40 degrees. Following the roasting, beans are reduced in coffee powder using industrial roller mill grinders. Aromas are partially released by the beans and collected by flowing nitrogen following a condensation of the aromatic vapors to be used later in the process. Brewing and filtering is performed mixing the coffee powder with hot water and high-pressure vapor to produce a very large cup of coffee. The spent coffee is separated, dried and burned to power the factory. The large cup of coffee is then submitted to evaporation, performed in giant tanks at 70 degrees. This phase condenses the coffee to 50% of its original volume. A syrupy kind of coffee extract is produced. The extract is frozen at a temperature between -40 and -50 degrees, and then it is again granulated while still frozen. The water removal by sublimation from the frozen granules is performed at 60 degrees in high vacuum chambers. The remaining water leaves the coffee granules by turning from solid to vapor. This is a fundamental step to remove the water excess, but not the aromas. Finally, the lost aromas collected by condensation during the process are given back to the dried coffee granules by a spraying technique. Important tasks during the instant coffee production are to provide coffee with a good taste and to rapidly and completely dissolve the coffee powder when added to hot water or milk. These features are strongly related to the microstructure of the coffee granules, their size, porosity, density and surface area. In a production quality control, it is necessary to have a rapid method to measure these important parameters. Open and closed pores might influence the aroma and the speed of dissolution. Thus, it appears quite important to have a reliable and possibly rapid analytical method to characterize the coffee granules. Micromeritics can contribute to the product and process optimization using three main techniques: Mercury Intrusion Porosimetry, gas pycnometry, and gas adsorption. Mercury porosimetry provides many pieces of information about bulk, envelope, and apparent densities, inter- and intraparticle pores, and, in some cases, also on inaccessible voids. This technique is not always suitable for rapid test during a production cycle because the sample preparation and the experiment are time-consuming. Additionally, additional laboratory safety standards for the presence of mercury and technician training are required for safe and proper use. Gas pycnometry can be a suitable test for rapid determination of skeletal density and does not require specific lab or expert users. Also, the surface area determination can be performed rapidly, but still requiring the use of liquid nitrogen and some additional expertise. We have understood that improving the production parameters is fundamental to have a better quality product in terms of taste and speed of solubility. Pore volume, size and shape play an important role, but understanding porosity in organic materials is not that easy. The sublimation process might leave some closed porosity and ink bottle pores with very narrow access, which can influence the solubility and the reabsorption of the aromas in the last spraying phase. Also, the residual quantity of water in the granules influences the shelf life. Let me introduce a few slides to describe rapidly the applied techniques: gas pycnometry, mercury intrusion porosimetry, and gas adsorption. Density is calculated dividing the sample mass by the relevant measured volume. There are several values of density that may be measured. We will focus on bulk and apparent density as measured by mercury porosimetry and skeletal density by gas pycnometry. The bulk volume is comprehensive of all open plus closed pores and voids between the particles. It can be measured by mercury porosimetry when the sample is under vacuum. The apparent volume is excluding open pores, and it is comprehensive of closed pores and pores that cannot be measured with the applied technique. For instance, mercury porosimetry has a lower limit of 3.6 nanometer size. Finally, the skeletal volume measured by gas pycnometry is the material volume comprehensive of only closed pores if present. Three cases can occur when comparing the skeletal density by gas pycnometry and the apparent density by mercury intrusion. The skeletal density is equal to the apparent density. There are no pores below 3.6 nanometer and the sample is pressure stable. If the skeletal density is lower than the apparent density, the sample collapsed, is compressed, or some closed pores have been opened by the pressurization. And finally, the skeletal density is higher than the apparent density. The sample has probably pores that cannot be measured by mercury porosimetry but are put in evidence by gas pycnometry. The gas pycnometry technique uses a gas displacement to measure accurately the skeletal volume of porous materials. Inner gases such as helium or nitrogen are used as the displacement medium. The material is placed in the sample chamber of known volume. The appropriate inner gas is admitted, pressure equilibrated, and then expanded into another calibrated internal reference volume. The pressures measured at the equilibrium in the sample chamber and expanding in the reference volume allow the computation of the sample solid phase volume. Helium molecules rapidly fill pores as small as 1 angstrom in diameter. Only the solid phase of the sample displaces the gas. Dividing this volume into the sample weight gives the material skeletal density. Mercury intrusion porosimetry is a well-known technique giving several information related to material porosity. Mercury intrusion begins under vacuum and can reach very high pressures up to 414 MPa. Due to these characteristics and to the assumption related to mercury intrusion, the results should be properly interpreted depending on the material under test. The total intruded volume might be relevant to the interparticle and or the intraparticle voids in case of powders. Organic material might be compressed, or the structure can collapse under pressure, revealing closed porosity. Finally, the minimum pore size that can be measured is about 3.6 nanometer, below which no information can be achieved and gas adsorption should be used. The presence of smaller pores or compression collapse can be validated by comparing the skeletal and apparent densities or by measuring the BAT surface area when applicable. Mercury does not wet most substances and will not penetrate pores by capillary action. Liquid mercury has a high surface tension and molecular forces on the surface film tend to contract its volume into a form with the lowest surface area. Consequently, entry of mercury into pores requires applying a pressure that is inversely proportional to the opening size. The higher the applied pressure, the smaller the pores to be penetrated. The intrusion pressure of mercury into pores is related to the pore size through the Washburn equation. Knowing the mercury surface tension and the contact angle between mercury and the sample, then the pore size range depends only on the applied pressure. Usually the lower applicable pressure is about 0.002 MPa and the maximum pressure 414 MPa, giving a measurable pore size range between 600–900 microns and 3.6 nanometers. In mercury intrusion porosimetry, we must consider that the main limitations are due to the high applied pressure and that the technique measures the pore size axis to which the intruded volume is associated. This will bring to a model of a bundle of capillaries, while real porous structures are much more complicated. Gas adsorption, more specifically physisorption, is probably the most widely used technique to measure the exposed surface area of solid materials and powders. It measures pore size in the micro and mesopore range up to about 300 nanometer. Gas adsorption is also widely used to measure very low surface areas, usually shown by macroporous or non-porous materials, and it is usually performed under isothermal conditions at cryogenic temperatures. Physisorption is a phenomenon that involves a higher density of gas molecules in proximity to solid surfaces due to the interactions of the molecules in the gaseous phase with the free surface energy of atoms and molecules in the solid interface. At a certain relative pressure below 0.3, a monolayer of molecules covering the surface can be determined using some theoretical model, being the BAT the most used. The BAT model applied in a range of relative pressure typically between 0.05 and 0.3 gives the number of molecules covering a monolayer. Knowing the molecular dimension of the gas, it is possible to calculate the total exposed surface area of the material. We'll expose now the results of these techniques applied to freeze-dried instant coffee. High-resolution skeletal density is commonly used to determine the purity of a given material or to assure reliability and reproducibility of a production process. Changes in the structure, in the composition, or in the porosity of a material are immediately observed by a variation of the skeletal density. This technique, using automated gas pycnometers, is generally very rapid. In case of instant coffee under our investigation, the helium pressure equilibration was extremely long. After more than 90 minutes, we could not get reliable results on the skeletal density. Long gas equilibration time after checking the leaks of the instrument are often due to the presence of closed pores that are accessible by helium with a slow diffusion process. In these conditions, the analytical parameters should be optimized because using the standard condition, the skeletal density may be variable depending on the number of analytical cycles. The first trial to solve the issue of long equilibration time is to reduce the gas loading pressure in the sample chamber. The standard procedure consists in performing the experiment at room temperature and loading the gas at about 230 kPa absolute pressure. That might be the reason of the slow diffusion. We reduced the loading pressure to 120 kPa. This is a typical procedure when testing closed cell forms. Unfortunately, also at reduced pressure, we had an equilibration time of more than 30 minutes, and that is not acceptable for our task. Sometimes it is useful to use nitrogen as measuring gas rather than helium when a diffusion limitation is present. Nitrogen is a larger molecule than helium and might not diffuse in smaller pores or cavities, making the analysis time reasonable. In case of this instant coffee, the situation improved a bit using nitrogen at 230 kPa, but still diffusion is present and equilibration requires more than 100 seconds for every cycle. Finally, we tried to use nitrogen at a reduced loading pressure of 130 kPa, finding the best procedure to shorten the equilibrium time. In this case, we obtained a density of 0.59 grams per milliliters, that is a relatively low value. Is this the real skeletal density, or we measured a sort of apparent density? If helium is diffusing slowly into the coffee granules, it might be possible that we have something like a closed structure. What we measured with nitrogen at reduced pressure is not the real skeletal density, because it might be excluding some closed cavities that nitrogen in these conditions cannot fill. We must investigate more. Mercury porosimetry is a very comprehensive method to investigate porosity, but the results should be carefully interpreted because of the assumption of the technique itself. In addition, very high pressures are applied and organic compounds are easily compressed or collapse. Analyzing dried coffee granules, the low-pressure intrusion occurs between the coffee particles, named interparticle porosity. These intrusion data can be used for particle size determination. But what about the intrusion at high pressure? Are there real pores at about 1300 nanometers? We need to compare the mercury porosimetry results of apparent density and surface area with the pycnometer density test first, and eventually with the BAT surface area. Mercury intrusion porosimetry, when performed with the proper analytical method and with a reliable instrument, is a very reproducible technique. In case of this instant coffee, the reproducibility on the total intruded volume is about 1%, on the pore size even better. The total surface area is about 9.5 square meter per gram, and the apparent density calculated at 414 megapascal is 1.66 gram per milliliter, much higher than the density measured by the pycnometer using nitrogen. Mercury intrusion provides for free also a measure of the particle size distribution. Intrusion at low pressure measures the cavity size and volume between the particles. This value is then converted to the particle size by using the Meyer-Stowe model. In this case, we have that particles at D50, 50% of the volume, are about 0.3 mm. This result is consistent with other sizing methods that have been applied to this coffee sample. The so-called skeletal density using nitrogen at reduced pressure was 0.59 grams per milliliter. We are not considering the density measured by helium because of the slow diffusion in the granules structure and never reaching the pressure equilibrium in a reasonable time at room temperature. The apparent density measured by mercury porosimetry at 414 megapascal is 1.66 gram per milliliter, a very high value, almost the triple of the density measured by nitrogen. This indicates that the sample might have an inaccessible porosity, slowly permeable by helium, but not by nitrogen at reduced pressure. Mercury at high pressure collapsed the structure, thus measuring what was before a closed porosity. Another useful information for the characterization of instant coffee is the specific volume of closed pores in the granules. Mercury porosimetry can provide with this information if a proper pressure cutoff is defined. At low pressure, left on the graph, we can measure the interparticle volume, while on the right side the intraparticle voids. This interpretation is valid whenever analyzing a powder material with intraparticle pores. By calculating the apparent density at a lower pressure and matching this value with the density obtained by nitrogen pycnometry, thus excluding the closed pores, we can get a proper cutoff value to distinguish the intra- and interparticle contribution to the total intruded volume. At 0.43 megapascal, the apparent density is 0.52 gram per milliliter, very close to 0.59 gram per milliliter by nitrogen low-pressure pycnometry. The inaccessible void volume inside the granules can be calculated also making the difference between the envelope volume measured by nitrogen, thus enclosing the inaccessible voids, and the apparent volume measured by mercury intrusion, when the structure is collapsed at high pressure. The void's specific volume can be also measured by the intrusion volume between the cutoff pressure and the maximum pressure. This last volume is a bit higher, probably influenced by some compression or packing effect. Another method to give the right interpretation to mercury intrusion data is to measure the BAT surface area using physisorption. Mercury porosimetry uses a very simple geometrical model to calculate the surface area, based on the calculation of the side area of a cylindrical pore with a known volume and access size. In addition, the surface area by mercury porosimetry is strongly affected by possible material compression or collapse. As these effects usually occur at high pressure, meaning small calculated pore size, the resulting surface is very high. Mercury porosimetry gives about 9.5 square meter per gram using all the data up to 414 megapascal. The BAT surface area on the instant coffee gives 0.26 square meter per gram, that is much less. In physisorption we use nitrogen at very low temperature, thus the possible diffusion of nitrogen into the closed voids is completely disadvantaged. Therefore, physisorption measures only the external surface due to the granule's roughness. If we calculate the surface area at the cutoff pressure that we have identified before in the mercury intrusion curve, we get an area of 0.28 square meter per gram, also by mercury porosimetry. This is another proof of the inaccessible void's presence. Some preliminary conclusions of the work done at this point is that mercury porosimetry is a good method to determine bulk envelope and apparent densities. In addition, it provides an indication of the inaccessible void volume, a bit overestimated due to some compression or packing effects. But mercury porosimetry is time-consuming and in this case might be more suitable for research purposes. The gas pycnometry using nitrogen at reduced pressure provides a quick method to measure the envelope volume, comprehensive of all the inaccessible voids volume and excluding the interparticle porosity. We still miss a rapid test to measure the real skeletal volume, thus we tried high-temperature pycnometry using helium. The purpose is to check if the diffusion of helium into the closed structure can be accelerated by the temperature, thus measuring a reliable skeletal density. As we can see, the higher temperature at about 60 degrees speeds up the diffusion of helium so that the skeletal density within about 70 minutes is stable. The same experiment using helium at room temperature could not provide a stable density even after 90 minutes running time. The skeletal density measured in this way is close to the porosimetry apparent density, confirming once more the presence of a closed structure. At this point we can say that on the instant coffee under examination, mercury porosimetry provides reliable information about particle size, bulk density enclosing all open, closed and interparticle voids, envelope and apparent densities calculated at different pressures, and the closed pore volume. Nitrogen pycnometry at reduced pressure measures rapidly the envelope density relevant to the open porosity and enclosing the inaccessible voids. Helium pycnometry at reduced pressure and high temperature measures the skeletal density because in these conditions helium can diffuse completely in the inaccessible structure. For the case of producing instant coffee by lyophilization, it is useful to define a single, rapid and reliable technique to measure envelope and skeletal densities and to determine the specific volume of the inaccessible voids probably generated during the freezing stage. Gas pycnometry performed with nitrogen at reduced pressure can rapidly measure the envelope volume of granules, that is the volume including all closed pores but excluding the interparticle voids. Mercury porosimetry can determine the inaccessible voids volume because the structure collapses under pressurization. The BAT surface area gives the final evidence to distinguish the interparticle porosity and the closed intragranules porosity. All the above results are synergic and can be applied whenever it is necessary to give the right interpretation and validation of mercury intrusion results. Finally, high-temperature pycnometry speeds up the helium diffusion into the inaccessible void structure, measuring in a reasonable time the skeletal volume of the particles. Knowing the envelope and skeletal volume of the granules, the inaccessible void-specific volume can be easily calculated. And thank you for participating, and I am happy to answer some questions now.
Thank you, Luca. I'm opening the chat for everyone's questions now, and we already have a few. Luca, when you were going through your helium pycnometry work, we noticed that you were using a relatively low pressure. Why not use a higher pressure to speed up the helium diffusion?
Thanks, Jeff, for the question. Yes, the main reason is that the standard pycnometer we have has a maximum loading pressure of 233 kilopascal absolute pressure. And the reason for this is that usually it is not, let's say, advisable to use very high pressure, not to modify the structure of the material under test. And then the other thing is that we have seen that there was no advantages even reducing the pressure or making the experiment at 130 kilopascal. So there was no, apparently, there was not a big influence of the pressure in the diffusion of helium into the closed structure.
Thank you. So there are also, So this is a, this is a freeze-dried product, and people have some concerns. What technique might be useful to measure the residual water content of the coffee?
Yes, there are several techniques. Normally, there are some instruments applying the Carl Fisher titrator that exploits a chemical reaction, a stoichiometric chemical reaction between the water content, SO2 and iodine. But this is a specific instrument. Alternatively, it is possible to use thermogravimetry by increasing the temperature, and the material release the water, and the weight change give you the percentage of residual water into the material, or also by temperature programmed desorption. By increasing temperature again, the material will release water vapor, and using a detector that can be thermal conductivity detector or a mass spectrometer, and through a proper calibration of the system, we can evaluate how much residual water is left in the organic material. So these are the most used techniques. I know also there are some thermal desorber, very quick, that they just use infrared radiation on the material placed under over a balance, so that by heating the water vaporize, and you can measure directly the weight change. So these are the most common use technique to measure the residual water in organic materials.
Today you gave us 3 really nice techniques for looking at some of these freeze-dried products. Did you have any special concerns about preparation of these materials before you measured density, porosity, and surface area?
Yes. First, for any result is referred to sample mass. So we must be sure that the sample is really well dried. So it is necessary to try to dry more the sample, maybe in an oven, or in case of a gas adsorption technique under vacuum, but never heating too much the organic material, because we might change the structure and so compromise and jeopardize completely the results. So yes, the answer is yes. Especially with organic materials, it is very important to be very careful in drying the sample, to be sure to have the right dry weight of the sample, because all the results are referred to the dry weight. Regarding gas pycnometry, apart from drying, then there are not specific sample preparation. Regarding mercury porosimetry, I would say that the instrument itself is performing a certain sample prep, because the material is placed under vacuum, and the analysis will not start until we reach a very good vacuum degree. So we are pretty sure that the material is absolutely dry. And the same occurs when we run a gas adsorption, because even in gas adsorption, before placing the sample tube into liquid nitrogen, so at 77 K, the material is kept under vacuum condition, and so we can be relatively sure that the material is dry. So, but quite a great care must be applied when drying the organic materials, because they are really sensitive to temperature. And the same is applied to pharmaceuticals, for instance, and all material that can be degraded by high temperatures.
So you gave us 3 very nice techniques for looking at these materials. Would it be easier to just apply BET surface area for them?
Let's say the BET surface area measure the exposed surface to the fluid. So for sure, it is an important parameter that is absolutely related to the speed of the solution, and also to the availability of the surface when in the last phase of spraying, the aroma collected during the process are given back to the granules. Now, all the presentation has been done by searching the production technique, searching on the web. I'm not an expert, of course, in producing freeze-dried coffee. I'm an expert in espresso, but I think that this surface area is very important, and for sure it is related to solubility and to reabsorbing the taste. But it is not the only parameter. I mean that during the lyophilization process, the internal cavities that can be generated by the freezing and then the sublimation drying create such an internal porosity, and that has an influence for sure in solubility and so on. So not only the surface area it is important to be determined, but also the closed porosity, the particle size as well, and all these results are synergic to understand better the process and to improve the product, as far as I understood about this complex technique of freeze drying.
Luca, on these products, have you ever used or have you ever seen anyone use CO2 instead of nitrogen for the adsorption studies?
Honestly, not. We didn't use CO2 to test the material. We just used because, let's say, at a certain point we solved the issue, and we can use nitrogen at reduced pressure to determine the envelope density of the granules. That is one of the important parameters. And then we just heating the sample at 60 degrees, we could diffuse rapidly helium into the structure to measure the skeletal density. So these two parameters rapidly and with a simple technique and without the use of let's say mercury porosimetry, because let's say in production is not let's say really suitable, could solve the problem. Okay, so could characterize. In addition, CO2, let's say, is not recommended for low surface area in case of the BAT, if the question is the BAT adsorption, because it's not forming a monolayer on low surface area materials. So it's more recommended to use nitrogen.
Thank you. Can you use a combination of mercury porosimetry and nitrogen pycnometry for determining the open and closed porosity of something like a soft, flexible cellular plastic?
Okay, plastics. It depends if it has, for instance, a closed porosity. Let's say if the plastic. It depends if the plastic is porous or not. If it is not porous, I would say that any gas, even helium pycnometry, will determine the density of the material, the real volume of the material. If it is porous, and there are no diffusion problems of helium, helium can be used to measure all the open porosity. Mercury porosimetry on this material, we have to take care that, or we have to check that the high pressure is not compressing the sample. In case of coffee, let's say there was not a big issue because the structure collapsed and we could measure the closed or inaccessible porosity. But in case of plastics, at high pressure, the plastic can be submitted to a reversible compression. And when we have a compression, usually it occurs at very high pressure. Very high pressure means very small equivalent pore size. And the small pore size means very high surface area. That is wrong. So, in our mercury micromeritics mercury porosimeter in the output, in our software, it is possible to correct the compressibility of material using some mathematical models. And but you always need the use of a gas pycnometer to, let's say, validate the pore volume that you measure by mercury intrusion, because this pore volume could be, let's say, jeopardized by the compression of the material itself.
Okay. So there's a follow-up question, and the follow-up question is just to be sure, And really two follow-up questions. So what's your main concern for using these soft foams with mercury porosimetry?
There is the soft?
Yes, if this is a soft material, what's your main concern for using mercury porosimetry with something like a soft foam, or even, I think the freeze-dried coffee that you showed is the same, maybe a similar material, that it's not as structurally stable as perhaps an oxide or other material. So what would be your main concern for using these materials with mercury intrusion porosimetry?
With this soft material, the main concern is always the compressibility or the structure collapse. And always, let's say we recommend whenever we test by mercury porosimetry samples for customers, or we recommend to customers always to check and to validate the result of mercury intrusion by helium pycnometry. Because as we have seen in one of the slides, the three cases can occur that when skeletal density and upper end density, they are the same, or one is higher than the other, can give immediately some indication on the fact that if the material is compressed or collapse, or if there is a porosity below the limit of mercury porosimetry, that is 3.6 nanometer.
Okay. And a very similar question, what would be your main concern with nitrogen pycnometry on these types of materials, these soft materials?
With nitrogen pycnometry, let's say nitrogen is, let's say, is a larger molecule, has a lower thermal conductivity, and in this case, it will not diffuse at reduced pressure into the post. In the example we have seen, when we use nitrogen at high pressure, at 230 kilopascal absolute, we got a density that was very similar to nitrogen at reduced pressure. So we got 0.61 grams per milliliter versus 0.59 grams per milliliter at 100 at reduced pressure. So it's very similar. The problem was that at this pressure, at 230 kilopascal, also nitrogen was slowly diffusing. So we could get a result, but still the pressure was not completely stable. That's the reason why we tried the nitrogen at reduced pressure. Of course, you never know. I mean, materials are not always the same, and they can have a different pore structure. They can have, let's say, a network of pores that is very complex, and therefore it's difficult to say something that can be generally valid for all the materials. But I would say that the only way is to try to modify the parameters that we can modify, like pressure or temperature or type of gas, and to use synergic and multiple techniques to validate the results. Because as we have seen, just using, for instance, gas pycnometry was not possible with helium, was not possible to get a skeletal density. And when we use nitrogen, we get a skeletal density to discover then that is not a skeletal density, because there is a close porosity that is too slowly measured by helium, and the nitrogen cannot enter. So, this is always, let's say, the concern to use multiple techniques, especially with organic material, because they are not really easy to be understood.
So, Luca, we've got one final question, and the final question for today is, these techniques, are these techniques good for research applications, or are they good for quality control, or are they good for both?
Okay, I would say that let's consider the three techniques. In gas pycnometry is very good for both. for research and quality control. It is rapid. We don't need very expert users. We don't need the specific lab organization and so on. And it is a very safe and known technique since a long time. For Mercury Intrusion Porosimetry, in some cases, it is a must. So you cannot avoid to use Mercury Intrusion Porosimetry even in quality control. But we have to consider that the person must be properly trained, not only to the use of the instrument, but also to the safe use of mercury, because let's not forget that mercury, in any case, it's a chemicals and should be treated in a certain way to avoid any danger for the operator. And but the analysis can be long, because let's say that the gassing is done in the instrument, is done at room temperature. So if the content of water is relatively high, it takes a long time to degas and to reach a good vacuum. Then also the intrusion takes time, because the point, every point in mercury intrusion must be taken at the real equilibrium. So depending on how many points we have, the analysis can be quite long, even because the pressure range is extremely high, as well as the pore size range is extremely large, because we start from visible pores, about 0.6 millimeters, and we go down to 3.6 nanometers. So it is the widest range. So we need many points. Every point is at equilibrium, so it's quite a long time. So I would say that, if possible, mercury intrusion should be more used for research purposes, but some cases it is the only technique that can be used in quality control. And finally, gas adsorption. Let's say when you need to measure just the BAT surface area, it's a rapid technique, because it can be measured by a single point analysis. It takes, let's say, apart from the sample preparation, it takes few minutes. You can have 4 or 5 points BAT measure, even in this case, maybe 1 hour. In less than 1 hour, you have a test, or can be used in research when we analyze microporous material or extremely low surface area, when we need the krypton and we need a complete isotherm to determine pore size distribution in addition to the BAT surface area. That can take a long time, even 48 hours, to have a complete experiment. So in this case, gas adsorption is better used of course, in research, because can be used in quality control where they need a rapid test.
Thank you, Luca. That's all the questions we have time for today. If you haven't been able to get your question, if we haven't been able to get to one of your questions, one of our applications team will be in contact with you shortly. Luca, is there anything else you'd like to mention today?
No, thank you, Jeff. I thank you. Thanks everybody for attending. It was the first time we studied this instant coffee, and I think it was really interested because it's a challenging subject. Organic material is always like this. So I enjoyed very much what we did on this instant coffee work. Thank you again to everybody.
Great. Thank you everyone for participating in today's webinar. If you have any feedback for us, we would be grateful if you could complete the survey, which will be distributed in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again very soon. Thank you and have a great day.